bit challenging, mostly because the software, much as they say it's supposed to work, it really gets kind of flaky with contacts, as I demonstrated in class. Basically, you're designing a mounting bracket for hydraulic cylinder with a fixed clevis end attachment. I'll talk about the brackets constructed of A36 that has been cut an appropriate size hole, machined, and welded to a flat steel base plate. You should make the steel plate large enough to disperse the stress concentrations before getting to the edge. And I'll even be really nice and say you can assume that the welds are going to make the part monolithic. That you don't have to have gaps between the welds or the plates or anything like that. Even though that's not really what happened, you get to assume that. Okay, so the rules are that in the horizontal position, and all of them go to horizontal, the cylinder must have a minimum of 5 inches clearances off the horizontal base plate. And then I give you information about the size of the cylinders. This is a website, but I also downloaded the catalog onto the Blackboard website. So you can go download the catalog off the Blackboard site. It has all the dimensions you'll ever need.
Nice.
Do you believe that?
No.
No, of course not. But it's going to be fun. Okay, so you're going to use the cylinders that you're going to design for. Are you going to use the fixed clevis ends, which is detailed on page 23. So, okay, and we'll talk a little bit about that later. Okay, you should design the bracket such that it has a safety factor yielding of 1.5 in tension and 1.3 in compression. Okay, it may be difficult to achieve these safety factors just by modifying the shape of the bracket. So let's look at these a little bit, and then we'll talk about how you can sort of tweak the design. So this is page 23. There's page 22 up here, right? So this is page 23. This is a clevis end bracket, and you see that there are different. This is all nicely sized here, depending on which size actuator you have. And I've gone through nicely and given everybody different size actuators. Oh, and Sophie, you got a big actuator.
Is it
So,
better?
yeah, 5 inch. I only went to 5 inch. So, got a big actuator. So it's can I say, you can't get good instructors. They always assign different ones, right? So it's okay. So everybody's randomly mixed on the size of the actuators they are. And obviously what you have is you have to design a part that goes in here, right? It goes into this fixed clevis end. And what does it have to do? It has to carry the force that the actuator pushes on it. Does that make sense? Now, the actuator, so obviously it has to be fitting around here, and on the bottom side here, I want a minimum of a 1/2 inch clearance off of the base plate. So you have to come up with a bracket, comes from the base plate, comes up in here, has a hole in it, right, that the pin can go in. Okay. Now you don't have to model the actuator. You don't have to model the pin. No contact stresses are not required. You can use a bearing distribution, and I'm fine with that. So you don't have to do contact stresses or anything crazy. I'm not going to get that weird on you. See, aren't I a nice guy? Nice is not the word you're going to use right now. But, okay. Anytime your professor gives an assignment, it's not going to be a nice. Nice is not the word that's applicable there, right? Okay. So anyway, here's all your sizes, depending on how big your actuator is, right? All the way down should be completely defined, or at least sort of completely defined. Obviously, things like the angles aren't always the best, but most of the time they're not going to matter for your design, mating parts. Okay, this is what the actuator looks like, and there's some more dimensions down here if you want to play with them down here. There's the rest of page 23. Okay, and so that's on the website. You can either download it from Parker or you can get it from Blackboard. I don't care. or you can steal it from your neighbor. Either way works. Is that gonna work for you guys? Well, no, it's not gonna work. Okay, so now let's look at this, what these things are gonna look like. We'll get back to the problem here. Okay, so your, the challenge is, of course, you have a base plate here. And then you have the actuator is going to fit in, something like this. Right, and you need to come up with something that, and I tell you how thick this is, right? I give you a T here. Okay, do I not give you a T? I think I say base plate thickness. Yes.
Oh, yeah, right there.
Yes, I give you a base plate thickness. Right. Yes. So okay, and then you get to build something that does something artistic like that because you think you're gonna do something like that.
Wait, what is that? It's a
Those are,
You're not liking that one.
scallops for lightning.
I have no idea why you chose to design it that way. I don't have a clue. So I got real skepticism on that one. Okay, so no one's gonna do it like that? Okay. So, how about like this? Okay, okay.
So you want 1/2 inch clearance on the left side.
1/2 inch clearance
This
here.
plate.
Okay, now, this thing, what's it, okay, then I give each of you a range of travel.
0 to 60 degree.
Okay,
60 degree.
they all essentially go horizontal, or at least I'm gonna say they all go horizontal. And then they bend up, right? Okay? Easy, isn't it?
Yes,
Okay, easy, easy, okay. So then what you do, obviously, this is going to make forces that either push on here or pull. Right, and if it pushes on there, what's it going to do? Well, it's gonna try to cause this thing to rotate. Right, and what are you gonna get? You're gonna get compressive stresses over here, right? And you're gonna get tension stresses over in here somewhere. Right? I think we can all see that just by sort of looking at it. We're gonna buy that, and of course, then you're gonna turn around and pull the other way. Now, do you push and pull with the same force?
The cylinder should.
No, it shouldn't. Why not? Well, when it pushes, you get the area of the piston. It's trying to get longer. You get the area of the piston. When it's trying to get shorter, you lose the area of the rod. Right? There's no pressure on the rod. No pressure pushing in on the rod. There's pressure all around on the rod, but that all cancels out. Doesn't help you at all. So the actual area you have to retract is smaller when you're retracting than when it's extending by the area of the rod. This is basically an annular area that you're subtracting when you're retracting, right? So the forces are different. Okay? I gave each of you pressures. Each of you have rod diameters. Each of you have piston diameters or bore diameters. So you can find all those forces. Because this is the smart, highly intelligent group that's gonna know that pressures and forces are not the same thing. Not like those UWB students. We all gonna buy that? We can all go like this? Yes, yes. Okay, so we all done. So anyway, okay, this is gonna push and pull on it. Now, if you have, that's going to give you tensions in this piece, and it's also gonna give you tensions in this piece down here, right? So both, you can have potential failures in this piece, potential failures in this piece, and there's a couple of things you can do about them, depending on how you feel. Well, you know, you can always, I guess, not do anything about it, but that makes it easy for me to grade. Okay.
Less privilege.
Okay, so one of the things, I let you have two possible options. Okay, one of them is you can place an intermediate plate in here. So you can go, hey, I don't like this thing going all the way down here. What I'm gonna do is I'm gonna put in something else, like this. Okay? And what that does is that thickens it up in that area, right? Thickens it up in that area, okay? And I say that, so you could put an intermediate plate in. The intermediate plate should be no thicker than the base plate, but may be significantly larger than the bracket. So you can grow it out in these dimensions. And I don't even insist that you follow the half-inch rule. So you can grow it out. What you're trying to do is to spread it out. Now, you still have to have clearance. You still have to be able to put the darn actuator on there, right? Because if you can't get the actuator on it, the whole thing is, yeah, it's just a big, ugly chunk of iron that someone is going to go after with a grinder, and then they're going to think really unkind things about the engineer who came up with that. Okay? You don't want that to be you. You want it to be some UWB students. Okay, okay. So that's one option. You can put an intermediate plate in there and sort of spread it out. It doesn't have to be as thick as the thickness of the base plate, but it can be that thickness. That allows you to shorten this up a little bit. And of course you can blend these together, and I expect cleverness on how to blend this together and make it look pretty. Now, the one thing I will say in all of this, okay, and I only have to say this to this group, this is not for Boeing, okay? Which means we're not going to take one giant piece of material and throw away 90% of it machining this, okay? That seems to be the Boeing way, okay? No, we don't do that, okay? Not going to do that here. What are we going to do? This piece is going to be welded to this piece, right? It's going to be a constant thickness piece, right? It's going to be welded down here because that's the way everybody in the real world outside of Boeing makes things, because otherwise it's too darn expensive.
Wait, the bracket's gonna be welded to the base plate?
Yep. Yep. Which means when you model it, what do? You go down and have 45-degree welds in it, right? Right, okay? Okay, that's because that's how it's gonna be made. That's how they're all made.
The only class in the whole country you have to tell this.
It is the only class in the whole country that I have to tell this to. Well, maybe not the only one. The Renton one would have to tell the same thing too. And then there's all these youngsters that because when, in the world outside of Boeing, how do we make things? We take constant thickness plate or constant thickness stock. We cut our shapes out of it, and we weld it together because it's quick and dirty and it gets the job done. That's sort of how things are made, for the most part. And the Boeing, I understand the desire to make things monolithic for machining them when they're on the airplane. Okay, you don't want stress concentrations, welds are bad, so you make that. But to have that carry on into things that are not on the airplane and are not subject to fatigue loads is one of the more interesting attributes of Boeing engineering, I will say. Right? right? That they seem to design everything like it's going to go on a plane and like it's going to be subject to fatigue loads, even when neither one of those things is the case. Am I wrong on that? You gonna disagree with me? You can disagree with me. You can go,
You're
no,
not
you're
allowed
full
to
of.
say.
What?
Confidential.
Oh, it's not confidential. You can walk around the plant and look at it. It's like, how many
Proprietary,
hundreds of thousands
proprietary.
of dollars did you spend on that you didn't have to? Okay. I mean, they're not exactly hiding them, right? They don't get stashed in the corners where nobody can see them. So I look at that and go, ooh, yeah, that was expensive, wasn't it? Yeah, it was. Okay, that's one option. Another option that you can do is you can go, hey, this base plate, it's deforming too much. What I'm going to do is I'm going to add in stiffeners down in here. Okay. You can add in stiffeners. Okay. You can put stiffening webs under the base plate, right? Okay. These stiffening webs should be no thicker than the base plate, but maybe up to 4 times as wide. So this has to be here, has to be less than or equal to T, where T is the base plate over here, right? But this one here and this dimension here, right, is less than or equal to 4T. Does that make some sense? So you're sort of constrained on how thick you can make the darn things, right? Okay. And if you put webs in there, they're used, you gotta leave clearance behind them for welding them, because what are they gonna do? They're gonna get welded in here, right? Okay. So now, and anybody who puts welds in that are 3 times the thickness of the plate is going to get scowled at by the instructor, right? Okay. So the stamp of disapproval, or as I told Taki the other day, I would be disappointed. So got me a nasty look from her. So that she still hasn't forgotten. I scared her where she wouldn't even come in today. So okay. So I'll pick on Taki. She's not here. Okay. So basically, there's a minimum spacing here. These have to be farther apart than the width of the weld. So this dimension in here, spacing dimension, can't be any thicker than that because you got to be able to get in here to weld them. Okay. So what you're going to give me, right, as an example, a short written description of the problem and proposed solution. Well, I think I've got a start of it there. Your FEA analysis is the design, loads and boundary conditions, stress plot for each load case. Okay, and then I need a drawing of your final bracket. Now, these can get quite interesting. And one of the reasons I will say, let's just talk about this a little bit. I'm going to go ahead and erase the actuator in here. Let's just talk about this a little bit. So let's say we have our bracket looks like this. And I'll draw it in black just to be nice so we can all see it. Our bracket looks like this, and we push on it. Like that. So what does it do? Well, it's going to give us real high stresses right here and right here. And we've all done that before because you had a bracket that almost looked like that. Right? So now what do you do with that? Well, we can weld it, right? And then what's it going to do? Still going to do the same thing. Right. So what I will let you do is go, oh, okay, hey, let's maybe over here, let's curve this out like this. Okay? Some nice curve like that, okay? And we can even do it on this side too. We can some nice curve comes out, and then what do we do? Then we weld it on there, okay? Now, let's think about this. Initially, what did we have is we had a stress concentration that was out, it was right in here, right where that corner was. Now, what's gonna happen on this one here in particular? What's gonna happen as I make this piece that goes out here longer?
You just increase the distance from the moment.
Well, as it gets out here further, right, I'm getting a stress concentration out here. As I make this get out here longer, what happens? Well, the moment arm gets longer, so the amount of force I need to push on it goes down, which means the stress goes down. And pretty soon, if I make this long enough, the stress concentration's not at the end, but it's gonna be somewhere else. And where else is it gonna be? Well, it's probably gonna be in here somewhere. Right? So you can move that stress concentration around. What you're doing is, as you make this go longer out here, and in particular if it's thinner, you're making it softer. Right? It's not as rigid. When it's not as rigid, it doesn't give you as big a stress concentration. Right? It's not giving you that great big stress concentration at the end. And so you can play with that. You can push the geometry out here to where you're getting the stress concentration in here, or you can go back and forth. Now, obviously, you probably won't have ones that are this simple. You're clever people. You're gonna come up with that fancy scallop design or some. I'm gonna get one that looks like a fish or something like that one of these days. So haven't seen it yet, but I'm expecting it one of these days for somebody that I've tormented with this one. So okay, so you can push these stresses around a little bit by depending on how you design it, right? And the thicker you make this, the more thicker you increase it, you'll take this stress concentration, move it further out here, because what are you doing? You're making this part more rigid. Right? And so you can play with the relative stiffnesses of these components. Is that making a little bit of sense? Now, obviously, you can make the radius bigger, you can make the radius smaller in there. You can play all kinds of interesting games with pushing out. You don't have to put a radius in there. You can angle it down. I mean, you saw what other people did, right? You can look online and see a zillion pictures of people who have done. Is this a new problem? No. They're all over the place,
So
right?
we need enough material at the end for the welds, right?
Yes, yes. Typically, there's enough material left at the ends for the welds, right? Okay. Now, otherwise, it's really not welded, right? And so now you can argue about how much of that you need to be there, right? So. Okay. So that's right. So you can either put plates underneath, or you can put an intermediate plate underneath, or you can do both, depending on what you feel like doing to either and or neither if you don't need them. Obviously, the easiest one is you don't have to do any of them, right? Just come up with a clever design for your bracket here, such that it meets the design criteria, and then you're done. You don't think it's going to be that easy? Nobody here thinks it's going to be that easy. So you think your instructor is going to have picked numbers that are evil? I think that's the only thing I've said that there's unanimous agreement on in class today, right? Okay, so that actually not all numbers are evil. Only some of them are. And I don't actually know which ones they are, but so.
Who do you hate?
They were somewhat randomly assigned, so I did say somewhat randomly assigned. Okay, so okay. So do you know what the problem is?
So obviously there's a force this way, but what are we gonna hold on to is the base plate?
Well, the base plate is going to become part of the machine, right?
Okay.
So, but we don't know quite what
Is
the
it
rest of the
long?
machine looks like.
Okay.
So what do? We do, and then these, we're gonna model the base plate as if it's attached to something much larger. So that we're worried about how the force gets from here into the base plate, right? And we're not worried about how the force gets from the load gets from the base plate out into the rest of the structure. That's the person who's designing the structure's job. We're not designing the structure, we're just designing the actuator attachment points. So typically what that means is we make the base plate big, and then we put boundary conditions around the edges, right, which we've done in the past. Right? In fact, this is awful lot, very similar to the problem that I gave you in the past. So you can go back and look at your models and go, did I give it in the past? Did I give this one in the past? Yeah, I did, right? So it's the, okay, so it's the, and so then now the only difference is you do have multiple forces, and yeah, you can. Well,
You make two sides of that, you're done. Just mirror it.
You only need one, right? One in the middle.
Oh, one?
Yeah, because we got clevis ends, right? So that our actuators have this,
Oh.
right? So our part has to fit in there, right?
I just do this one.
This, so isn't it easy?
Hand it in to you.
So it's an easy problem? Yeah, see, it's,
What did you mean that how the forces are different in pushing and pulling? I didn't quite follow.
well, when you're pushing, you have an actuator,
Yeah.
which has a cylinder bore, has a piston, and then it has a bore, right? And then there's a rod in it. So when you're pushing,
And you're giving us different rod diameters, it looks like, and a fixed pressure, so, yeah.
everybody's got a pressure and a maximum pressure
Oh,
and,
I think I get it.
right,
You can't
right.
increase the pressure to make it up the difference on the other side.
Well, typically the system pressure is decided. It's a constant. It's what the pump is capable of outputting or what the relief valve on the system is designed for, right? The system has an operating pressure. And for the most part, actually, I've made the problem much easier for you guys than the last group I had. I was not so nice to the last year's group, so I lowered everybody's pressure down, so.
Lower the standards for us.
No, well, I wasn't trying to lower the standards, I was just trying to reduce the anxiety, shall we say. You gonna buy that one? Not any more than the other one I was buying, right? Okay, so, yes, again, yeah, when you're pushing on it, you get the whole area of this. When you're pushing this way, you'll lose the area of the rod, because there's no hydraulic force on the area of the rod, right? So so it's an easy calculation, you just have to remember that's the way it works. So the forces are not the same going each direction, right? And then, of course, obviously, you have to worry about them, are they horizontal, or is this case the worst, and you don't know which one is which, right? You don't know which case is going to be the worst, right? So now, obviously, it's not doing all of the loads at the same time, right? It's an actuator. It's either pushing or pulling, and it has an orientation, right? It doesn't have multiple orientations at the same time, so there's only one force on it, right? And now maybe at different angles, but it's one pushing force and one pulling force. Right? Okay?
What website did you say you should go to then?
It's on the,
Mine is unloaded from.
it's,
It takes a lot of load,
the Parker one does?
yeah.
It's-
Yeah,
it's
'cause I
slow.
started going down and it was all blank.
Oh, okay, oh yeah, it's 26 megabytes, and it is on Blackboard in the FEA class, so.
I'm trying to download it from there.
From Blackboard?
It
Yeah,
comes from
oh yeah, it's gonna be, well, if everybody's trying to download it about the
Yeah,
same
you gotta
time,
give
it's,
it a-
we're probably chugging the network right